Okay, so welcome back to the last lecture of today. And it's my pleasure to introduce Professor Stefano. He received PhD from CISA, Italy, under the supervision of Stefano Bianchini. And he joined the group of Laszlo in University of Leipzig for a postdoc. Then he joined the Technological University of Darmstadt in Germany as an assistant professor. And currently he's a professor at GSSI in L'Aquila. It's pity that he could not come here because of some reason. So today he's going to speak on PDEs associated to a non-smooth vector field. So Stefan, over to you now.
So thank you very much for the kind introduction, also for the invitation to give this talk. Unfortunately, I couldn't be there in person. I really regret that because I think it has been an amazing workshop. I followed something online, what I could find online. So unfortunately, I had a recent moving to a new apartment exactly in this period with the whole family. So it was really difficult for me to travel in this period. Okay, so let's start with the mathematics. So this will be a very informal talk. So I think it's late afternoon there, so you are probably tired. So you won't see any proof essentially in this talk. It's just so the goal of this talk is to provide quite informal overview on some problems, some questions, and some answers to problems related to non-smooth vector fields. In particular, so as the title says, to flow maps and PDEs related to non-smooth vector fields. So let me start by just fixing some notation and going to the first slide. So, okay, just to fix the notation, so I will use the notation U for a vector field, which for me is a function of time and space with values in Rd. The space here is the periodic domain for simplicity, but many things I will say applies to the full space or the bounded domain. So, but let's just assume that we are on a periodic domain. And so the title says I'm going to talk about a non-smooth vector field, but let us first of all talk about a smooth vector field. To see what happens in the smooth framework, and then we will see what we can say, well, how we can extend the smooth theory to the non-smooth one. And by smooth here, I mean essentially as typical when you deal with vector fields, I mean Lipschitz continuity in the space variable. So there is some constant L such that this relation, this Lipschitz continuity in space holds uniformly in time. You can also assume that this constant L depends on time and is integrable with respect to time, but that's not really relevant. So let's just say uniform in time Lipschitz continuity in space. Now, what you do when you have a vector field, the first thing you do is to consider the ordinary differential equation associated to this vector field. So you pick some starting point, x0 in your domain, and you consider the ordinary differential equation, the ODE, associated to U. So gamma dot of t equal to U of t gamma of t, with the value at time zero of your solution being this fixed point x0. And we all know that under this assumption, there exists a unique solution to this ordinary differential equation that we will call trajectory or characteristic starting from the point x0. Then, of course, what you can do is you can repeat this procedure for every starting point x0. So for every initial point, you build a characteristic, and then this defines what is typically called the flow map. So a function of time and space with values in space as well, where this capital X is nothing else than the solution to this ODE, in the sense that the second variable, the X, denotes the starting point of each characteristic. So as a function of time, this map capital X is the solution to this ODE starting at time zero in the point X. And again, so under this assumption, this flow map exists, is unique, and it is well defined. It has essentially the same smoothness as the vector field. So in particular, it's Lipschitz continuous in the space variable and even smoother in the time one. So it's a very nice map. Okay, so far so good concerning the flow map. Okay, and the title says flow maps and PDEs, so partial differential equations associated to vector fields. So there are essentially two partial differential equations that you associate to a vector field, and they describe two physical phenomena. So let me briefly describe. So this is stuff that essentially everybody in the audience knows, I'm pretty sure, but it's just to fix some notation and then to make some reference for what's going on in the next. So let's say that we have a function rho, function of time and space with values in R, some scalar function. And then, so we want to use this function to describe two different physical phenomena that in principle have nothing to do with each other. So the first one is what we can call the transport. So in this first column of the table, so the transport, what does it mean? Let's say that this function rho describes, I don't know, the quantity of some contaminant in the air produced by some factory. So at any time t, the function rho as a function of x is how much contaminant is in the point x at time t. And then it's reasonable to assume that this contaminant is transported as a passive scalar, transported by the flow of the air. So this means that the contaminant that you have at time 0 in the point x must be the same as the contaminant at time t in the point where the particle located at time 0 in x stays at time t, so in capital X of tx. So this is a passive transport, transport of some passive scalar. And it is well known that in our smooth setting of this slide, this relation is equivalent to saying that the map rho satisfies this well-known PDE, which is the transport equation. So typically in PDEs, one gives the PDE and then says that this is the solution. I took somehow the other way around. So I started from the physical phenomenon I want to describe, and then which is encoded in this relation, and then I derived the sort of the PDE from that. So this is one physical phenomenon corresponding to the transport equation. And then the second one that one might want to describe is the conservation of mass. So I assume that this map rho now describes the density of mass of some fluid, for instance, again at any time t as a function of x. So it's density of mass at time t of your fluid. Then you expect this mass to be conserved, which means the following. If I take some subset omega of my physical domain, the periodic domain, and I compute what is the mass of the fluid inside this domain, inside this omega, I have to integrate the density at time t as a function of x over this domain omega. Now, conservation of mass means that if I trace back so the subdomain omega to the time 0, so I look at all particles which at time t are in omega, I look back at the place where they were at time 0. So I look at the pre-image through the the flow map at time t of the set omega, and I compute, so I integrate the density at time 0 with respect to x over this domain, I should get the same number. So this is conservation of mass. Now you see that this map capital X for any fixed time is a function from space to space. So I can take the pre-image, which is this set, and then I can do this integral. And now in a more mathematical form, this equality, if this equality holds for every Borel set, this is equivalent, it's exactly the definition of saying that this density, if we think to this map as the density of some measure absolutely continuous with respect to the Lebesgue measure at time t, this density is equal to the push forward of the initial density through the flow map at time t, fx time t as a function. So this flow map again as a function from space to space. I have some initial density here. I push it forward at time t through the flow map, and I get the new density at time t. So this is conservation of mass. And again, in a smooth setting, it is well known that these two equalities are equivalent to saying that the map rho satisfies this other PDE, which is the so-called continuity equation. Now, in principle, these are two different physical phenomena, the transport, the passive transport, and conservation of mass. Nevertheless, at least on a formal level, if the divergence of the vector field is 0, so if our vector field is incompressible, then these two equations are at least formally equivalent, and in a smooth setting, they are equivalent. So in this talk, I will assume that they are indeed equivalent, and in fact, they are very much related from a mathematical point of view. So I will talk about one or the other in the same way. I will not make any difference between the two equations. Okay, so I mean, I cannot see the whole audience, but if you have any questions or anything, just so feel free to interrupt me at any time. Okay, so far so good for the smooth setting. This is the classical theory. Let's say what happens in the smooth setting. And now the goal of this talk is to present, to discuss a little bit what happens if you relax the smoothness assumption. So the smoothness assumption was this Lipschitz continuity in space. So relaxing the Lipschitz continuity means typically that either you go for Hölder continuous functions, where you reduce the number of derivatives that you control, or you look for Sobolev, so for vector field in Sobolev spaces, where you do not reduce the number of derivatives that you control, but their integrability. Okay, so but the first thing that I want to do is okay, we want to relax the vector field, but we have to understand what kind of questions we can ask in a smooth setting. So let's go then to the next slide. So again, now let's say that we have a vector field just without any regularity assumption for the moment. Just let's assume incompressibility, but many things I will say applies also when this incompressibility assumption is somehow relaxed. But let's just assume that our vector field is incompressible. And what I want to discuss now is so what kind of questions can one ask in a weak setting? And by weak setting, I will mainly focus on the Sobolev case, not the Hölder continuous case, because somehow you see, even from the classical example that you learn in calculus 1, like x dot equals square root of x, it's pretty immediate that for a Hölder continuous vector fields, there is not much that one can do. So it's quite easy to find a counterexample to well-posedness and so on. So somehow, I will think more of this relaxation of Lipschitz in terms of Sobolev regularity of the vector field. Okay, so what kind of questions can we ask? And let's discuss that, first of all, in the case of the ODE. We have this ODE, gamma dot equal u of t gamma, with initial datum gamma of 0 equal to x. The first thing is, what is a solution? If U is not smooth, it's just a Sobolev or whatever, what is a solution? And the answer here, okay, so this is the PDE. I will discuss later the PDE, just the LaTeX, in the LaTeX it popped out before, but let's focus on the ODE now. So what is the solution of the ODE in a weak setting? Well, for me, a solution will be essentially a solution in the integral sense. So I map a function of time with values in TD, a curve on our domain, on our flat torus, which satisfies the ODE in the integral sense, gamma of t equal to x plus the integral from 0 to t of the vector field integrated along the solution. So this is the definition of solution. And then, okay, now that we have a definition, what kind of question can we ask? Well, the first immediate question is the question of pointwise existence and uniqueness of solutions, of characteristics. So given a point x, is there a solution to this ODE? Is this solution unique? Or more in general, we can ask, so can we characterize the set of points for which there exists a unique solution to this ODE? For instance, can we say that existence and uniqueness of solution holds for almost every point? So can we say that the set of points where existence and uniqueness holds is a full measure set? Or can you show something else? Can you characterize this set? So this is the first question. It's sort of a natural question that you can ask in a weak setting. But then there is a different kind of questions that one can ask, more sophisticated one. And it's the following, what we can call the existence and uniqueness question in the selection sense, which means let's forget about existence and uniqueness pointwise. So we don't care whether for every point, for almost every point, there exists a unique solution to this ODE. We don't care. We just ask whether for almost every point, we can select one solution. So there is at least one solution, and we can, for almost every point, select one of these solutions in such a way that this family of solutions that we can denote with this notation capital X of Tx, in such a way that this selection of characteristics, this family of solutions that we selected, makes sense. And what makes sense means will be clear later. But I just want to stress now the kind of question that one might ask. So we forget about pointwise existence and uniqueness, and we just focus on the question whether it is possible to select for almost every point one characteristic in such a way that the whole selection that we made, the whole family of characteristics that we selected, makes sense in a suitable sense. So it's reasonable in a suitable sense. Okay, so far so good for the ODE. And now let's discuss briefly what kind of questions we can ask in the case of the PDE. So this is again the PDE. I just brought down the continuity equation because, as we said, under this incompressibility assumption, this is equivalent to transport. So let's just focus on the continuity equation. And again, as for the ODE, the first thing we want to do is to say what kind of solutions we are looking for. What is the definition of solution that we are using? Well, there is a natural notion of solution in this case. So the equation is naturally written in a divergence form. So we can look for distributional solutions. And in fact, so essentially for me, weak solution to this PDE means distributional solution. There are other notions of solutions. We will talk about one of those notions later. But okay, for the moment, a solution is just a distributional solution. It's the most natural notion of solution of a PDE in a weak setting, so distributional solution. And then, okay, once we have the notion of solution, again, what kind of questions we can ask? So what is the question we can pose? How can we phrase the question? We can phrase the question in this way. So assume that we have some Banach space, capital X. For instance, this capital X can be some LP space, the space of Radon measures, or some other space, whatever. So we have some reasonable Banach space. We have an initial datum, so an initial density, which belongs to this Banach space. And then we want to show, or we ask whether there exists a unique distributional solution, ρ, which stays at any time t in this Banach space X uniformly in time. This is like a natural question for a PDE, in particular for this PDE. For instance, okay, we have an initial datum in LP, and we ask whether there exists a unique distributional solution which is uniformly in time LP in space. Okay, so this is essentially the question for the question for the PDE. And I want to make two observations. The first one is the following. So in order to define a distributional solution, we must be sure that the product ρu, which appears here, is well defined as a distribution. For instance, we must be sure that this is an L1 log function, locally integrable in time and space. Otherwise, this product does not make sense as a distribution, and we cannot define distributional solutions. And the fact whether ρ times u is makes sense as a distribution depends very much on what is this Banach space that we pick, and what is the space where our vector field u lives. For instance, if u is just a locally integrable vector field and ρ is a locally integrable density, then the product is not locally integrable in general. So we cannot define distributional solutions. So there is some attention we have to pay here when somehow stating theorems and looking for solutions. And then the second observation that I want to make, and I will come back on that also later, is that somehow for the PDE, the real question is the uniqueness of solutions. The existence of a weak solution is a quite easy task, and this is essentially due to the fact that this PDE is a linear partial differential equation. So finding one solution by compactness is not really difficult. I will come back on that later. And the real issue is the uniqueness question. Okay. So far, so good. This was, okay, so for the ODE, we have these two questions, the pointwise existence and uniqueness, and the existence and uniqueness in the selection sense. These are two different questions. For the PDE, we have somehow the classical existence and uniqueness question in some Banach space. Okay, so now I'm going to discuss some more in detail, some answers to those questions, and essentially, I will divide the rest of the talk into parts. I will first discuss what we can call the classical theory, which is almost more or less 30 years old. And then I will discuss towards the end of the talk the more recent developments of this theory. So let's start then from the classical theory. And the classical theory, so the most part of classical theory was developed by, so let's go to the next slide, was developed by Ron Di Perna and Pierre-Louis Lyons in their paper in 1989 on invenciones. So this paper here. And before, stating the theorems, the main theorems that they proved in this paper, let me point out what are, in my opinion, three of the main ideas present in this paper. Okay, the first idea is what we have somehow already mentioned before. So at the beginning, we said we want to relax the Lipschitz continuity. And we can do that either by assuming Hölder continuity or by assuming Sobolev continuity. But Hölder is clear that it's not the correct way to relax the Lipschitz continuity. So let's go for Sobolev. Well, this idea of looking for Sobolev vector fields was the best of my knowledge for the first time introduced in this paper. And so this is the first somehow main idea, look for Sobolev vector fields. Then the second main idea is something that we have also already mentioned, and it is the idea of saying, okay, let's forget about pointwise existence and uniqueness of solutions to the ordinary differential equations, but let's look for existence and uniqueness of solutions to the ODE in this selection sense. So is it possible to select one characteristic for almost every point in such a way that the whole selection makes sense? This is the second somehow main ideas. So they introduce this notion of selection sense that I will make precise in a second. And then the third idea is the following. So we have seen that in the classical setting, in the Lipschitz setting, what you do is you have the ODE, you solve the ODE, and then you use the solution to the ODE, so the flow map, to solve your PDEs, either the transport or the continuity equation. So you solve the ODE and you solve the ODE and you use the ODE to solve the PDE. Now, the third main idea in this paper of Di Perna-Lyon is the fact that so you can do the opposite. So in a weak setting, you can use the PDE. You can first analyze the PDE, and then you can use what you know on the PDE to prove results on the ODE. So they reverse the point of view, essentially. Okay. So in fact, so in this paper of Di Perna-Lyon, they treated both the PDE part, so the continuity and transport equation associated to Sobolev vector fields, and the ODE part associated to Sobolev vector fields. Let's start with the ODE part, and let me tell you finally what it means, this selection sense. So let me give you a precise definition of, so one possible precise definition of what it means selecting characteristics in a way that makes sense. And I will not exactly follow the definition of Di Perna-Lyon. I will follow the definition introduced by Ambrosio 15 years later in 2004, because somehow this is a simpler definition and it was the one that was then afterwards mainly used in the literature. So the definition is the following. It's the definition of regular Lagrangian flow. So what is a regular Lagrangian flow? This is, by definition, it's a map, function of time and space with values in space, as the classical flow, essentially, such that two properties hold. The first property is what we would expect from a flow. So for almost every initial point, the flow map, so for fixed x as a function of time, this is a curve in our physical domain, and this curve solves the ordinary differential equation gamma dot equal u of t gamma with initial point x. So for almost every point, this regular Lagrangian flow must be a solution to the ODE, And this is somehow natural to expect from something that we want to call a flow. So this is a selection of characteristics, okay? And then so what does it mean that they make sense? Well, to be a regular Lagrangian flow, there is a second property that this map acts to satisfy, and it's the following. So the push forward of the Lebesgue measure through the flow map at time t, so once again, for fixed t, this map X is a function from TD into TD, so from space to space. So we have the Lebesgue measure here. We can take the push forward through this flow map here. And then, okay, the requirement is that this push forward measure is less or equal than some constant L, some fixed L, independent of time, times the Lebesgue measure itself. What does it mean concretely? It means that it's equivalent to say that for all Borel subsets of the torus, you take your Borel subsets, you take the pre-image through the flow map. So you look at all particles that are sent by this flow map into omega. You trace them back at time 0. And the requirement is that the measure of the initial set must be less or equal than L times the measure of the final set, which means, roughly speaking, that so a regular Lagrangian flow cannot send a very large set into a very small set. So you cannot send a very large set at time 0 into a very small set at time t. There has to be some control on how much this flow map can compress sets. Okay. So this is the definition. So a regular Lagrangian flow is a map which satisfies these two properties. Clearly, in a classical setting, in the Lipschitz setting, the standard flow map is a regular Lagrangian flow. Okay, so this is the definition. And what Debayan and Lyons and Ambrosio later, I will again state the next theorem in the Ambrosio formulation, what Debayan, Lyons, and Ambrosio proved in terms of the ordinary differential equation for this notion of regular Lagrangian flows, so this selection of characteristics which makes sense, is the following theorem. So they proved that. So assume that you are given a vector field which is incompressible. This can be relaxed, but we don't care. But no further assumptions. So we don't assume Lipschitz, we don't assume Sobolev, we don't assume anything. So let's just pick a vector field, so incompressible with no further assumption. Then let's assume that, so if for every initial datum, so for every initial density in L infinity, there exists a unique distributional solution to the PDE, to the partial differential equation, so to the transport equation, which stays in L infinity of time and space. So if for every initial bounded density, there exists a unique distributional solution in the class of bounded densities. If this is true, okay, then there exists a unique regular Lagrangian flow for you. So you see, from this theorem, this is claiming essentially nothing concretely, but it's saying that if you have a vector field for which you can show something at the level of the PDE, then you can translate this information into an information for the ODE. And more precisely, if you have existence and uniqueness in L infinity for the PDE, then you have existence and uniqueness for the regular Lagrangian flow. So once again, this is not saying anything on pointwise existence and uniqueness of characteristics. It's just claiming existence and uniqueness of this selection map, this regular Lagrangian flow. But if you have something at the level of the PDE, this implies something at the level of the ODE. And then, okay, this is very good because now we have reduced our problem to a PDE problem. So now we can just pick our favorite vector field and we can ask whether we can show this well-posedness, so existence and uniqueness for the PDE in the class of L infinity. If we can do that, then the ODE problem is essentially solved in this selection sense. Okay, so let's go then to the next slide. And so we've reduced the PDE problem. And then what Debayan and Lyons in their paper proved at the PDE level is the following theorem. So, okay, I will state now a more general theorem that what is needed to apply the theorem of the previous slide. So I will state a sort of purely PDE theorem, and then I will comment on how we can apply that in order to recover something for the ODE, as we have seen in the previous slide. But let me state this theorem in a purely PDE form, so in its most general form. The theorem is the following. Assume that you have, so let's forget for the moment ODE, just PDE. Let's pick an exponent p between 1 and infinity. We fix an exponent p. And let's assume that we have a vector field which is L1 in time with values in W1 P prime in space, where P prime is the dual holder to P. So 1 over P plus 1 over P prime is equal to 1. So a given vector field in this class, in this Sobolev class. Then, for every initial datum in LP, there exists a unique distributional solution to our PDE with that initial datum, which lives where? Well, the solution lives in L infinity in time with values in LP in space. So the solution is LP in space uniformly in time. Okay, this is a purely PDE theorem. It's a well-posedness theorem for the PDE. I will say some words on the proof later on in a second, but before doing that, let me make a couple of remarks. So the first remark is that, first of all, we mentioned before that we need to make sure that this term makes sense in the sense of distribution, this rho times u. And the observation is that in order for it to make sense, it's enough to have u, which is L1 in time, LP prime in space, because you see, the rho is L infinity in time, LP in space. So if u is L1 in time, LP prime in space, the product is L1 in time and space. So it makes sense as a distribution. Now, what the theorem is saying is that if your vector field is not only here, but it's also the derivative is in this space, so if the field is W1P prime in space, then we can prove existence and uniqueness of solutions. But in order to define distributional solution, somehow this is enough to make sense. So this would be enough. So this is the first observation, the first remark. The second remark is that Ambrosio, that we have already mentioned before in 2004, extended this theorem to the case P equal infinity, which in the Perna-Lyon's theorem would correspond, you see, for P equal infinity, P prime is 1. So the Perna-Lyon will say, give me a W11 vector field, then I have existence and uniqueness in L infinity, L infinity. And Ambrosio extended this theorem to the case of BV vector fields. So W11 means derivative in L1, BV means derivative a measure, a Radon measure. So this is an extension to the class of fields whose derivative is a Radon measure. Okay, and last observation that I want to make is thinking back to what we have said in the previous slide. So we said that the previous slide, there was a theorem saying if you can show existence and uniqueness for the PDE in L infinity, then there exists a unique regular Lagrangian flow. And so the observation is that if I pick P equal infinity, so I consider really the class of L infinity densities, then the Perna-Lyon would say that it is enough to have a vector field in W11 or even BV, thanks to Ambrosio's theorem. So if we have a vector field in W11 or even in BV, then by combining this PDE theorem to the general principle that we have seen in the previous slide, we get existence and uniqueness in L infinity for the PDE, and therefore existence and uniqueness of a regular Lagrangian flow. So somehow summarizing from the PDE point of view, this is the statement. For the ODE point of view, what the Perna-Lyons and Ambrosio are claiming is that if you have a Sobolev vector field or even a BV vector field, then the ODE is well posed in this selection sense, so in the sense of regular Lagrangian flow. Okay, so let me say a couple of words about the proof of this theorem of the Perna-Lyon, this PDE theorem. I'm not saying anything about the connection between PDE and ODE because that's quite so it's a harder task in a sense. But let me say something about the PDE theorem. And so this is not a proof, of course, just a couple of words about that. So concerning the existence. Okay, for the existence, as I mentioned before, the existence is a very easy task. In fact, it is enough to assume this condition. So it is so once we are sure that the product rho times u is well defined, and we have said that this is some of the class that we need, the combination of classes that we need to make sense of this distribution, then existence is fine. And the reason is that how do you prove existence? You take your equation, you regularize the vector field, you regularize the initial datum. Now everything is smooth. You apply the classical theory, the Cauchy-Lipschitz theory, you get a solution. You have a family now of solution depending on your regularization parameter, and you want to show that this family is compact. But what kind of compactness do you need? Well, you just need a weak compactness because the equation is linear. And weak compactness is quite easy to obtain because you just need a uniform bound for the solution itself and not for its derivatives. So existence is a quite easy task. I hope I convinced you of that. And then the main question is about uniqueness. And cheating a little bit, we can say that the question of uniqueness is, okay, existence we get by compactness, so by subsequences. And uniqueness would, morally speaking, mean that we can show that every subsequence has the same limit. I'm cheating a little bit, but morally speaking, this is that's it essentially. And then how do you show that this limit is unique? Well, the proof is based on a commutator estimate, which runs as follows. So we have said you take your equation and you regularize the equation somehow. Now you see that when I take my equation and I multiply by a modifier, then I get, this term is linear, so I get the modification of rho. And then when I modify this product, I don't get the product of the two modification, but I get somehow the modification of the product, and then I can add and subtract the product of the modification in order to have on the left-hand side a classical transport type term, so the transport of this modified guy with respect to the modified field, and then on the right-hand side I have some error term. And somehow showing that this limit that I get by subsequences is unique, so every subsequence is the same limit, amounts to show that this commutator, so this error goes to zero strongly as epsilon goes to zero. And how do you show that? Well, first of all, since the vector field is incompressible, I can put this derivative on the rho part. So I get gradient of rho epsilon times u epsilon minus gradient of rho times u modified. And then it's standard when you have a modifier, so when you have a commutator, that somehow the key property of a commutator is that you can move the derivative on, which is on one term, you can move it on the other term. So somehow this is equivalent to rho times the derivative of u. And now you see why these assumptions are needed. If rho is L infinity LP, and u is L1 W1P prime, which means that the gradient of u is L1 LP prime, then this term is well defined. Now this commutator is rho times gradient of u times a little o of 1, something which goes to zero as epsilon goes to zero. And now you see that as far as this stays uniformly bounded, and that's the case if rho is L infinity LP and u is L1 W1P prime, if this stays uniformly bounded in epsilon, then I can pass epsilon to zero, this goes to zero, and then I get this strong convergence to zero, which guarantees the uniqueness. This is, of course, not a proof, but somehow this computation, I wanted to do this computation because I wanted to point out that it is crucial that the integrability of the density and the integrability of the derivative of the field somehow match each other in order for this product to make sense, and then in order to conclude the proof. Okay, so far so good for the PDE. Let me just make a last remark, I mention it because it's quite important result. I don't have time to discuss it. And the remark is that, okay, so what I showed you is that you take your PDE, you use PDE techniques, so commutator estimate, to show something on the PDE, and then you use the PDE result, which is of interest by itself, but then you use your PDE result to go back to the ODE and prove existence and uniqueness of the regular Lagrangian flow. The remark I want to do is that you can also develop, it's possible to develop a purely Lagrangian approach, a purely Lagrangian theory, in the sense that you can not consider the PDE, you just take your vector field, you regularize the vector field, you consider the flow map, the classical flow map associated with the regularized vector field, and then it's possible to show that this family of flow maps at the Lagrangian level, at the ODE level, has some compactness property, and that the limit is indeed a regular Lagrangian flow. This has been developed by Kripp and Ellis in 2007. I didn't write the year, it's 2007. And unfortunately, it works just for p bigger than 1. And you can guess why, because there is some harmonic analysis tool involved. And then p equal 1 and p equal infinity are critical. But p infinity, so I should have written p prime, because somehow this is the exponent of the field. I meant, okay, so the integrability of the field has to be bigger than 1. So infinity will be Lipschitz, so of course everything works. So the critical case is W11. And in fact, this is not covered by this theory. Okay, but I don't want to enter to give more details about that. I just wanted to mention this. Okay, so far so good for the, let's call it the classical theory. So what has been developed by Debayan in 1989 and then later on by Ambrose in 2004. And this is a sort of a positive theory. So they proved positive results, existence, uniqueness, well-posedness, and so on and so forth. And now, so in the next part of the talk, in the last part of the talk, let me discuss some more recent theory for both for the PDE and for the ODE. Some theory which has been developed in the last 5-6 years. Okay, and as we did before, first of all, let's try to summarize and what we have done so far, and let's try to understand what kind of questions are left open and what kind of question then we can ask. Let me start from the PDE. So the general question is, can we go beyond Deterministic? What I mean by that? Well, Deterministic was saying that so that if we look for densities which are LP, I mean L infinity in time, LP in space, but I just write now the space dependent. So densities in LP and vector fields which are W1Q with 1 over Q plus 1 over P plus 1 over Q equal to 1. So Q equal P prime or less or equal than 1, which is even better. Then we have uniqueness, existence and uniqueness of solutions to our PDE, to our transport or continuity equation. And then the natural question that one can ask is what happens if 1 over P plus 1 over Q is strictly bigger than 1? Okay, so this is the kind of question that is left open after Deterministic. And there have been, I mean, recent developments about this question. I will mention in the next slides. Now, what about the PDE? So let's summarize what we have done. I mean, the general question for the ODE will be whether uniqueness holds or not almost everywhere. In what sense? Well, once again, what we have seen by combining somehow the Deterministic theory and the Ambrosius one is that if we have a vector field which is solvable for some Q between 1 and infinity, or even a BV vector field in the Ambrosius theory, then combining the PDE part with the ODE part, we have existence and uniqueness of a regular Lagrangian flow. I remind you that regular Lagrangian flow means a selection of characteristics which makes sense. We have seen in what sense, but just to which makes sense. So uniqueness, existence and uniqueness of a regular Lagrangian flow does not mean in general that we have existence and uniqueness of solutions to the ordinary differential equation for almost every point. It just means that for almost every point, we can pick one solution. So there exists at least one solution, but there can be more than one. There can be 2, 3, infinitely many. Uniqueness of the regular Lagrangian flow just means that we can, for almost every point, we can pick one of those solutions in such a way that the whole family, the whole selection makes sense. So the question is that, can we show more? So can we, for instance, characterize the set of points for which there exists a unique solution to this ODE? Can we say, for instance, that it is a full measure set or not? Can you say something more? Okay, so this is somehow the two questions. For the PDE, going beyond Differential. For the ODE, existence and uniqueness in this point-wise sense and not in the selection sense. Okay, I will start the discussion starting from the PDE part once again. So let me go to the next slide. So PDE part. So uniqueness and non-uniqueness for the transport and the continuity equation. Let's recall the setting once again. This is our PDE. I assume incompressibility for simplicity. And I'm looking for a density which is L infinity in time LP space, a vector field for a given vector field which is L1 in time W1Q in space. And Differential is saying that if 1 over P plus 1 over Q is less or equal than 1, then we have uniqueness. And we are asking what happens if 1 over P plus 1 over Q is strictly bigger than 1. This is the setting. Now, what kind of answers have been provided in the recent year? Well, the first answer is what I got in a series of joint works with, so some of them with Gabriel Zattig, was a PhD student in Leipzig, and now he is finished, and I think he's not continuing the academia currently, and with Laszlo Zekelidi, that you know very well because he gave beautiful lectures in your workshop. So we showed that actually non-uniqueness can happen if this duality, 1 over P plus 1 over Q, is strictly bigger than 1 plus 1 over D, where D is the dimension of the physical space. So you see, this is not covering the full complement of Differential, which will be just 1, bigger than 1. But if this is bigger than 1 plus 1 over D, then we can show non-uniqueness. And once again, you see that it is crucial, this relation between the integrability of the density, which is this P, and the integrability of the derivative of the field, which is this Q. So if they do not match, as in the Differential theory, then we can show non-uniqueness. And the proof is done by convex integration. Okay, so I will not mention how the proof goes, but now, so you know many things about convex integration, so it's done by convex integration. Okay, more recently, there have been further answers to this question, but in order to state them properly, I need to introduce some new notation, some new notation, and I'm going to do that in the next slide. And the next slide will be a little bit technical, so I apologize for that. I need to introduce the notion of superposition solution. I will try to go slowly, but it will be a little bit technical. So what is this notion of superposition solution? Let me first introduce some notation, easy notation. I will denote by gamma the set of all continuous functions from time with values in the torus. So curves on our domain, continuous curves on our domain. And I put the uniform convergence topology. So this is a very nice Banach space. Cool. Okay, and then I will denote by gamma x, where x is a point of the torus, of the domain, the set of those curves which solve the ODE starting in x. This set, in principle, for a given vector field may be empty, maybe, so U is a given vector field, so this set may be empty, may contain a single element, may contain more than one element, infinite many of them, whatever, we don't know. So given the vector field, this is a well-defined set for every x. Okay, and now let's give the definition. The definition of superposition solution is the following. So a weak solution, let's say that we have a weak solution to the partial differential equation, to the continuity equation, which is L infinity in time with values in L1 in space. I could pick also, I don't know, the space of Radon measure or some other LP. I just give the definition in the case of L1 for simplicity. So assume that we have a weak solution, so a distributional solution to the PDE, which lives in this class, with some initial datum rho 0. There is a 0 here missing. So with some initial datum rho 0 in L1. Then we say that this weak solution is a superposition solution if there exists a family of eta x, depending on the parameter x, which is the point on the torus, such that, so what is this family? I tell you in a second. So two properties hold. The first property is that for almost every x, this eta x must be a probability measure on gamma. So gamma is a Banach space. It has the topology of Borel subsets, or the sigma algebra of Borel subsets. So I can put probability measures on that. And the requirement is that for almost every x, this eta x is a probability measure on the space of curves concentrated on gamma x. So concentrated on the set of solutions to the ODE located in x, starting in x. So I am implicitly assuming that this set is non-empty, that I have at least one characteristics. So essentially, this eta x is telling me how likely it is that I follow one characteristic rather than another. Of course, if gamma x contains just one single element, if there is just one single characteristic starting from a point x, then this eta x must be a Dirac delta concentrated on that curve. But if I have more than one characteristics, this eta x is telling me how likely it is that I follow this path rather than this or that, and so on. And then, okay, the second property is essentially, roughly speaking, saying that this weak solution rho is transported by the characteristics of the given vector field U according to these probability distributions. In what sense? Well, in the following sense, that for all t and for all smooth functions on the torus, the integral of rho at fixed time t in x against phi, so this duality, is equal to what? Well, you take phi, you compute it at gamma of t, where gamma is any curve, and then you integrate over all the space of curves according to this probability measure eta y for fixed y. This gives you a number depending on y, and then you integrate it weighted with the initial density. This could look quite mysterious. I will make an example in a second hopefully to make it more clear. But somehow what this is meaning is that rho is transported by the characteristics of U according to this family of probability measures. So let me do an example. Let's assume, for example, that we know that our vector field for almost every x, there exists a unique solution to the ODE. Okay, a very happy situation, very nice situation. And let's call this solution with the usual notation, capital X of x, where this x is the starting point and this is the time variable. Okay, so let's assume that for almost every x, we have a unique solution. So this set gamma x is a singleton for almost every x. This is the case for smooth vector fields, for instance. Okay. Then, as we were mentioning before, there is only one possibility for this eta x. It must be, it's a probability measure concentrated on a singleton. It must be a Dirac delta on that singleton. There is no more choice. Okay. And then if we try to write down what is this formula, when this eta is a Dirac delta, so if eta is a Dirac delta on a single curve, this integral over gamma is nothing else than phi computed in the point capital X of Tx. So this integral over gamma against eta becomes phi computed along the unique characteristic starting from x at time t. And then, okay, I still have this rho zero here, and I have the integral of the torus. Whereas on the left-hand side, I have exactly the same term. So if you write down this equation 1 in this very simple case where gamma x is a singleton, then you get this relation. And this relation is once again nothing else, if this holds for any time t and for every test function phi, is nothing else than saying that rho of t, so the density rho at time t as a function of x, is the push forward through this flow map, capital X of t, of the initial density. So exactly the same formula that we have seen in the classical case. So this example is saying that in the special case where you have existence and uniqueness for almost every point for the ordinary differential equation, in this very, like in the smooth case, then this formula is saying that your rho is somehow push forward, is transported, is the transport of the initial density along these unique characteristics. And now, in the general case where we don't know whether we have a unique characteristics for almost every point, this is saying that you have some initial density, and this density moves along the characteristics, but in principle, it does not move in a unique way, but so somehow density located in the point Y moves a little bit along some characteristics starting from Y, and then a little bit along some other characteristics, and so on. And how much it moves along each single characteristic starting from Y is given by this probability measure eta Y. And then at time t, you reconstruct your picture after moving the initial density along all possible characteristics weighted with these probability measures, and then you recover your density rho. So a weak solution is a superposition solution if there exists some family of probability measures doing this job, such that rho is transported along the characteristics according to these probability measures. Okay, there are two remarks I want to add, which are not immediately useful for the PDE that we were discussing in the previous slide, but let's keep them in mind for the next slide. Okay, the first one is that, so two remarks to keep in mind for the ODE part, the last slide. So the first remark is this implication that assume that you know, as it was the case in this example, or it is the case in the smooth setting, that you know that you have almost everywhere uniqueness and existence for the ODE. Then this gamma X is a singleton, as in the example, then there is no choice for the eta X, it must be a Dirac delta. And this means that any superposition solution must be given by this formula, which in particular means that you have PDE uniqueness in the class of superposition solutions. So the almost every uniqueness for the ODE implies the PDE uniqueness in the class of superposition solutions. And conversely, if you have a vector field and you can show that you have non-uniqueness in the class of superposition solutions, then this implies, by the converse implication, non-uniqueness of solutions for the ODE on a set of positive measures. And this will turn out to be important in the last slide, number 10. And then the second remark that I want to do is the following. Okay, very nice, but how do we show that a solution is a superposition solution without having to find all these probability measures? How do we show that? Well, there is a nice sufficient criterion, which is known as Ambrosio's superposition principle, which says that every weak solution which is positive is necessarily a superposition solution. It's not an if and only if, okay? But if you have a solution which is positive, then it must be a superposition solution. So in particular, let's say that we are able to show a PDE non-uniqueness in the class of positive densities, then this would imply non-uniqueness of the ODE on a set of positive measures. Okay, so let's keep in mind these two remarks for the last slide, for the last slide number 10. Let me go briefly to the slide number 9, where we were discussing, this was the state of the art that we were discussing before. So uniqueness and non-uniqueness for the PDE, and I mentioned this result of myself in collaboration with Gabriel and Laszlo, where we show non-uniqueness of weak solution under this partial complement of Piperna-Lyon. And then I promised two developments. Well, the two developments are in the class of superposition solutions. Sorry, I'm running out of time, so I kindly ask if I may have 5 more minutes maybe to conclude. Okay, so in the class of superposition solutions, Brouet, Colombo, and Bellellis showed that uniqueness holds. Now, the class of superposition solution is a smaller class than weak solution. So showing uniqueness is somehow easier in the sense that, for instance, they could extend the Piperna-Lyon, okay, a little bit. So they could show that if 1 over p plus 1 over q is less than 1 plus some other exponent, which is this one, then you have uniqueness of solutions, once again, in the class of superposition solutions. And in the same paper, they also showed non-uniqueness in the class of superposition solutions, which is now more difficult because it's a smaller class, so showing non-uniqueness is more difficult. They showed non-uniqueness in the class of superposition solutions by convex integration in the same range as these works of mine with Laszlo and Gabriel. Okay, and very recently there has been some developments in the non-uniqueness setting, where so Brouet, Colombo, and Kumar, I think the paper was so this year, so very recently, they showed that actually non-uniqueness holds in the exact complement of the set where uniqueness holds, once again in the class of superposition solution. So if 1 over p plus 1 over q is bigger than 1 plus, again, this exponent, so it's the same exponent. So in the class of superposition solution, the problem is fully solved. There is uniqueness below this threshold, there is non-uniqueness above this threshold. And what is interesting is that this proof is no convex integration. So it was not done by convex integration, but it's really the sort of explicit construction of one counterexample. So there is no this flexibility, this so huge amount of counterexample that you get by convex integration. It's the construction of one specific counterexample where you can see that. Okay, and so let me spend maybe one or a couple of minutes. So this is about the ODE. So this was the recent theory, the more recent developments for the PDE. And let me say something about to conclude about the ODE. Now, if you remember, the question was, so let's recall the setting. We have our ODE, and we have a vector field, which is a Sobolev for some q between 1 and infinity. Of course, infinity does not make sense because it's Lipschitz continuous. So, but okay. Then we have seen that by Dipernal, Lyons, and Ambrosio, we have existence and uniqueness of a regular Lagrangian flow. So existence and uniqueness in a selection set. And then the question that we wanted to ask is, let's consider the set of points for which there exists a unique solution to the ODE, okay? And this existence and uniqueness of the regular Lagrangian flow tells us nothing about this set. And we want to ask, for instance, whether this set is a set of full measures. So can we characterize this set in this sense? Is it a set of full Lebesgue measure? And well, there have been also here important answers, which essentially completely answer this question. The first one is by Caravenna, Laura Caravenna and Gianluca Crippa in 2018, where they answered positively. So they said, yes, it is a set of full Lebesgue measure if the Sobolev integrability of the field is bigger than the dimension of the space. So this is the dimension of the physical space we are working on. Okay, so if Q is bigger than D, then there is a unique, so this set is a full Lebesgue measure. So there is, for almost every point, a unique solution to this ODE. And then in the negative, so what happens for Q less than D? Well, there have been, in the same paper I mentioned before by Brouet, Colombo, and Lellis, they proved that in general the answer is no. So this set might not have a full Lebesgue measure if Q is less than D. Okay, and somehow the proof here is by convex integration plus the application of this Ambrosio superposition principle. In what sense? So they showed in this paper by convex integration that there is non-uniqueness in the class of positive densities. Now, positive densities are by Ambrosio superposition principle are superposition solutions, but the non-uniqueness in the class of superposition solutions for the PDE, we have seen it means that the set where you have existence and uniqueness cannot be a full Lebesgue measure set. So there might be, the set where uniqueness does not hold must have positive Lebesgue measure. Otherwise, if this is full Lebesgue measure, if this is full Lebesgue measure, then there can be a unique superposition solution. So they used convex integration at the PDE level combined with this theory of Ambrosio of superposition solutions to show non-uniqueness of, so to show that this set in general does not have full Lebesgue measure. And this was improved then later by Pichko and Sorella, I'm not sure about the year actually, where they show that not only the set E might not have a full Lebesgue measure, but it can also have a Lebesgue measure equal to 0. So it can happen that for almost every point there is non-uniqueness of solutions to the ODE if Q is less than. And then, okay, so somehow there is a very recent development by Kumar. So you see that in this theory of Coulomb and Dell'Ellis, the vector field is a Sobolev and nothing else. But you can ask, okay, let's say that your vector field is a Sobolev and of course not Lipschitz, because otherwise everything will be well defined, but let's say Hölder for some alpha less than 1. Then can we say something? So is the combination of the two giving us some more information? Well, actually the answer is no, because Kumar showed in 2023 that this set E, again, might have a 0 Lebesgue measure, even when the vector field is a Sobolev and C alpha for Q less than D and for any alpha less than 1. So that's somehow the optimal setting of exponent you can think. And once again, this is no convex integration, but it's really an explicit construction. Okay. And with that, I stop here. So I thank you very much for your attention, and I'm open to questions.
Thank you, Stefano, for excellent talk. Any questions or comments?
On the slide number 8, when you are defining superposition solution, so suppose that lambda x, if this is like gamma, capital gamma x, if this is like finite set, so how it look like the neta x?
Okay, so this is a definition. Okay, so we say that rho is the superposition solution if this family exists. One possibility now, let's say that instead of looking for L1 densities, you look. Let me make this example, which is maybe more clear. We look for densities which takes values in the set of radon measures. Okay, so our density might be like concentrated on one single point. Okay, now let's say that you have two characteristics starting from the same point. Okay, then you can, and your initial datum for the PDE is a Dirac mass located at this point. Then one possibility that you have is that when time evolves, you send 1/2 of the Dirac mass along one characteristics and 1/2 along the other. Okay, and then your density at time t will be 1/2 the Dirac delta in one point plus 1/2 the Dirac delta in the other point. Okay, this is a pretty admissible, it's a pretty nice solution. I mean, measure value, it's not L1, but you can adapt the example to make it L1. So this is a measure value solution to your PDE. Okay, and somehow the corresponding family of probability measures is essentially 1/2 the Dirac delta on one characteristic plus 1/2 the Dirac delta on the other characteristic. So with probability 1/2 you follow one line, with probability 1/2 you follow the other trajectory. I hope I answered the question.
So I have a question, Stefano. So if you are not in the class of superposition solution, how far you can go in the complement of the Fernalion setting?
Okay, so if you combine what's written here with the Fernalion, you see that so if you are essentially above this threshold, then they showed non-uniqueness in the class of superposition solutions, which implies in particular non-uniqueness of weak solutions, because superposition is a subset of weak solutions. So the only range which is somehow still open is the intermediate range between the Fernalion and this exponent, okay? Where in the class of superposition solution, there is uniqueness by this result. So the question is whether there exists some weak solution in this intermediate range between 1 and this exponent. There exists some weak solution which is not a superposition solution. Now, the problem, this is open to the best of my knowledge. And the problem here is that it's, as far as I know, it's quite hard even to construct weak solutions which are not superposition solutions. Okay, because there is only this sufficient criterion of Ambrosio. If the solution is positive, then it is a superposition. But there is, as far as I know, no necessary criterion. Okay, so showing that a weak solution is not a superposition solution is not so easy. Okay, but let alone somehow combining this with some non-uniqueness of weak solutions which are not superposition. And there are some examples of weak solutions which are not superposition solutions, but they are examples concerning a very rough vector field. I mean, a very, very rough vector field. I can make you an example which was mentioned to me by Paolo Bonicato. And the example is the following. So assume on the real line, 1D example, you have, imagine now, I don't remember exactly how you can make it precise, but assume that you have like a subset which is dense, and also the complement is dense. Okay, you can imagine something like that, like Q and irrational, but it's better if they both have positive measures. So let's not be too precise. Now your vector field is 1 on the set. It's 1D example, so just a number, the vector field. It's 1 on this set and -1 on the complement. Okay. Now this vector field cannot have characteristics, because as far as you have a characteristics, you don't know whether you should go to the left or to the right, because immediately you hit points where the vector field is +1 or -1. So there is somehow the set gamma x, the set of characteristics is empty. But you can define a density which is minus the field. So it's 1 where the field is -1, and it's -1 where the field is 1. So the product rho times u is identically 1. So it is a stationary solution to the continuity equation. But there is no, so there are no characteristics. So in particular, there cannot be it cannot be a superposition solution by the simple fact that there are no characteristics. So you have nothing to transport on. Okay, so this is okay, but you see it's a very rough example. So this vector field has no regularity at all. Okay, so for Sobolev vector fields, constructing a weak solution which is not superposition, I have no example in mind in this moment.
Thank you. Okay, so if there are no more questions, so let's thank Stefano again for this talk.
Okay. Thank you very much for the kind invitation.
Thank you, Stefano.